Lecture 13 is Alkynes. This is chapter 9 from Wade. This is the last real material that we're going to be covering in first semester. Our last lecture, lecture 14, is going to be a little primer on synthesis and the logic and strategy and a little bit of history of organic synthesis. But we're going to be wrapping up our first semester of organic chemistry, talking about formation and physical properties and reactivity of the triple bond, which in nomenclature we call alkynes. So we're going to be looking at several reactions of alkynes. And as you can see here on this reaction map, we're going to be accessing some new functional groups that we haven't seen before. We're going to be able to convert alkynes into carboxylic acids, ketones, aldehydes, as well as polyhalogenated products, including alkenes. We're going to be able to make cis and trans alkenes, and we're going to be looking at how to use vicinal and geminal dihalides to make alkynes. We're also going to be doing one very important and unique transformation that involves formation of a carbon-carbon bond. You'll see here, this is a 3-carbon alkyne, and we can transform it into, among other things, a 4-carbon alkyne. This is the first time in our 9 chapters that we have been able to make a carbon-carbon bond. All of the other bonds that we made have been from carbon to some other heteroatom, like an oxygen, a bromine, chlorine, for example. The crux of organic chemistry, of course, is making new molecules, is creating new complex, say, natural products from smaller, more basic and cheap and widely available starting materials. And inevitably, the way you do that is by making carbon-carbon bonds. So there are, as we will see, only a handful of ways to do that. Only a handful of ways to make a carbon-carbon bond. And in chapter 9, lecture 13, we will encounter the first of those. So alkynes are what we call hydrocarbons that contain carbon-carbon triple bonds. We mentioned that sometimes alkenes are called olefins because they are derived from olefin gas. Alkynes are sometimes called acetylines because they are derived or are derivatives of acetylene, which is the simplest alkyne. This is acetylene right here. It's a 2-carbon alkyne. Clearly, that's the smallest, simplest alkyne you can have. The common term is acetylene. It's also, you would call it ethyne in IUPAC. This is ethylacetylene. You can see how this is simply acetylene, where we have replaced one of the hydrogens with an ethyl. Or here's dimethylacetylene, where we have replaced both of the hydrogens with methyls. We could also call this 1-butyne. It's a 4-carbon chain with a triple bond, so butyne. And you'll notice that the triple bond starts on the first carbon, so we call it 1-butyne. This would be called 2-butyne. Again, it's a 4-carbon chain containing an alkyne, so butyne. But the double bond starts on the second carbon, so it's 2-butyne. The chemistry of the carbon-carbon triple bond is similar to that of the double bond. We're going to see that many of the addition reactions and oxidations that we saw with alkenes are parallel for alkynes. There might be one extra step involved in the mechanism, or you might get double the amount of product that you had with alkenes, but that is simply due to the addition, the inclusion of another pi bond in the reaction. There are, however, some reactions that are specific to alkynes, and they depend on the unique characteristics of the triple bond. And sometimes, in a certain case, they will depend on the unusual acidity of the acetylenic carbon-hydrogen bond. By that I mean this carbon-hydrogen bond right here is unusually acidic. And we're going to look at why that is and how we can take advantage of that. Let's start with nomenclature. It might not be surprising, but nomenclature of alkynes is similar to nomenclature of alkenes in that you start with the longest continuous chain of carbons, and we're going to try to include the triple bond in it as often as possible. We're going to change the ane ending of the parent to -ine. We saw that before, butyne and ethyne. We're going to number the chain from the end closest to the triple bond, and we're going to designate the position of the triple bond with a number, and we're going to choose the numbering system to give the lowest number possible on that triple bond. We're then going to give substituents off the main chain numbers to indicate their locations. That should seem pretty standard based on all the nomenclature that we've done so far. So in this example, we've got a 7-carbon chain. 1, 2, 3, 4, 5, 6, 7. And it's got a triple bond, so it would be called heptyne. Now, we would number it from left to right because we get to the carbon-carbon triple bond on the 3rd carbon as opposed to the 4th carbon if we number it left as opposed to right. So it's not just heptyne, it's going to be 3-heptyne or hept3-ine. Then we would have a methyl on the 2nd carbon and a bromine on the 6th carbon. So it would be 6-bromo, 2-methyl, 3-heptyne, or 6-bromo, 2-methyl, hept3-ine. I'm going to include in this lecture a brief discussion of naming alcohols along with a class of molecules called alkynes, because in a number of these reactions that we do with alkynes, we will also be making alkenes and also be making alcohols. So it's often the case that we will have these functional groups together on the same molecule. And in that case, it can get a little messy depending on whether we are naming a molecule with an alkyne and an alcohol, or an alkene and an alkyne, or perhaps an alkene and an alcohol, or perhaps all 3 of them. So for alcohols, the hydroxy name for alcohols is part of the old, more common naming system. In IUPAC, rather than using hydroxy, what we do is we use the ol suffix, and that will take priority in naming. Now, what I mean by that, I can show you through examples. Here is a 4-carbon chain that contains a triple bond, and it has an alcohol on it. So having a triple bond in the main chain of 4 carbons, this is a butyne. But it's also got the alcohol, and we're going to use the alcohol as a root that takes priority over the alkyne. So instead of naming this as, say, a hydroxy butyne, we're going to name this as 3-butyne-2-ol. You see that we are making the ol as the root now. And the butyne is also part of the root, but we are making the ol at the end of the root. We're basically giving it higher priority, making it the root of the root, if you will. Now, in terms of numbering, because the alcohol gets priority in the root, it's also going to get priority in the numbering. So we're going to number this carbon chain from left to right. 1, 2, 3, 4. That gives our 4-carbon chain with an alcohol on the 2nd and the triple bond on the 3rd. That's why it's 3-butyne-2-ol. If you want to split the root even further, you could call it but3-ine-2-ol. And now you can kind of see why splitting the root is nice, because it gives you the number directly before the name referring to the functional group. So but, 4 carbons with a 3-ine and a 2-ol, a but3-ine-2-ol. You might call this an alkynol. It's an alkyne alcohol. So keep that straight. Alcohols take priority over a triple bond when the two are on the same group. Let's look at triple bonds and double bonds. You might call this an alkene. It's got an alkene and an alkyne. Here, look at the name. 2-methyl, 1-pentan-3-ine, or 2-methyl-pent, 1-N-3-ine, an alkene. So what are we doing here? Notice we're doing the exact same thing as we did with the alcohol, but we're giving priority to the alkene. So here's a 5-carbon chain, 1, 2, 3, 4, 5, and we would number from left to right. That gives priority to the alkene. That gives a 1-ene and a 3-ine with a 2-methyl. So it's a pentyne, or it's a 1-pentan-3-ine, or pent 1-N-3-ine with a 2-methyl. If you have an alkene and an alcohol, we would call this an alkenol, generally speaking. But look at the name, pent 3-ene-2-ol. So here the alcohol gets priority. So we've got a 5-carbon chain. We're going to number with priority for the alcohol, so right to left, 1, 2, 3, 4, 5. That's a 3-ene and a 2-ol. So pent 3-ene-2-ol. And specifically, this is the E isomer of the double bond. So we'll put E in front of it. Now, to summarize what we're seeing here, because this is pretty complicated, for numbering the chain, alcohol takes priority over alkene, which takes priority over alkyne for the numbering. So here again, we gave priority to the alcohol over the alkyne. Here we gave numbering priority to the alkene over the alkyne. And here we gave priority to the alcohol over the alkene. So for numbering, alcohol, alkene, alkyne. For the name, the order in which the groups are appended is ene, ine, ol. So notice in the name here, we have ine first and then ol. Here we have ene first and then ine. Here we have ene first and then ol. So ene will always come first, then ine, then ol. If we have an alkene and an alcohol, we'll skip the ine. We'll just go ene, ol. If we have an ine and an ol, we'll skip the ene and we'll just go ine, ol. So that's weird because there's different ordering. Don't ask me why that's the case. That's just the way that it is. So your job is to figure that out, to memorize that or remember that in some way, and then apply it, especially if you have a molecule like this, where we have all 3 functional groups. So take a moment to try to name this. Remember the priorities that we saw. For numbering, it's all over N over ine. And for ordering in the name, it's ene, ine, ol. So give this a shot. You can pause the video and try it on your own. Okay, hopefully this is the name you got. This is E, 4-methylhept, 3-ene-5-ine-2-ol. So let's go through how we got that name. First of all, it's a 7-carbon chain. We have 1, 2, 3, 4, 5, 6, 7. A 7-carbon chain. And for numbering, we're going to prioritize the alcohol. So we're going to number from right to left. 1, 2, 3, 4, 5, 6, 7. If we do that, that means that we have an alcohol on the 2, an alkene on the 3, and an alkyne on the 5. So we can order that in terms of the name as the ene, then the ine, then the all. So we have a 3-ene, 5-ine, 2-all on a 7-carbon chain. So that's hept 3-ene, 5-ine, 2-all. Then don't forget the methyl group. We've got a methyl on the 4-carbon. So it's 4-methyl, hept 3-ene, 5-ine, 2-all. And lastly, don't forget the double bond. The geometry of the double bond always needs to be specified unless it's at the end of a chain, in which case it doesn't have E or Z designation. But in this case, it's in the middle of the chain, and this is an E double bond. The alkyne would have the number 1 priority on the left carbon, and the carbon would have the number 1 priority on the right carbon over the hydrogen. So this is the number 1, this is number 2. Those are on opposite sides of the double bond, so it's an E. Again, notice how logical it is to split the root like this. Instead of saying heptene or heptyne or heptanol, it's just hept 3-ene, 5-ine, 2-all. You just split the root and put the name immediately after the number that tells its location. Substituents always go in front still. So you have sometimes a choice as to whether you want to make a substituent named as a substituent. For example, make an alcohol, an OH, as a substituent and call it a hydroxy group, or if you want to make it part of the root and make it a heptanol, a heptan 2-ol, for example. We can do more naming like this in workshop. There's lots of naming examples in Stromanus as well. So the geometry of alkynes is different from the geometry of alkenes. Remember that in alkenes, we had pi density above the plane of the sigma bond and below the plane of the sigma bond. And that's because we only had 1 pi bond, and so that pi bond had to be in a certain plane. For example, these yellow balloons are always, let's say, in the Z plane. They're always up and down. So if that was an alkene, that's where our density would be, above the plane and below the plane. But for an alkyne, to get that second pi bond in there, we have to use another pair of p orbitals. And of course, p orbitals sit perpendicular to one another. So we have 2 pi bonds in our alkyne, and they sit perpendicularly to one another. We got the pi bond above and below the plane from the yellow balloons, and we've got pi bond in front of and behind the plane of the sigma bond in the pink balloons. That essentially means that no matter where you're looking around this molecule, you're going to see pi density. It looks more like a sphere, or it looks more like a cylinder of pi density around that carbon-carbon sigma bond. In terms of electron potential map, it would look like an egg. We've got most of the pi density towards the middle. That would be between the 2 carbons here. We have density above the plane of the bond, below the plane of the bond, and in front of the plane of the bond and behind the plane of the bond. Triple bonds are shorter than double bonds, which are shorter than single bonds. Again, the more electron density that you have between the 2 atoms, the closer those atoms can get to one another before they start to feel the repulsive effects of the positive charges from their nuclei. So when you only have 1 pair of electrons between the 2 atoms, they sit at 1.54 angstroms. When you have 2 pairs of electrons between the carbons, they sit at 1.33 angstroms. And when you have 3 pairs of electrons between the 2 atoms, they sit at 1.2 angstroms. Notice that the corresponding carbon-hydrogen bonds are also shortened. In the sp3 carbons, the carbon-hydrogen bonds are 1.09 angstroms. In the sp2 hybridized carbon-hydrogen bonds, it's 1.08 angstroms. And in the sp hybridized carbon-hydrogen bonds, it's 1.06 angstroms. This is because the orbital that these carbons are using to make the sigma bond to those hydrogens have more S character. In sp3, it's 25% S character. In sp2, it's 33% S character. And in sp, it's 50% S character. So those higher S character orbitals are more spherical, and that allows the electrons to sit closer to the carbon. That makes the bond shorter. They're less elongated. Remember, pi's p orbitals are very elongated. S orbitals are nice and kind of small and spherical. So the more p character we have, the more elongated those bonds will be. A related outcome of that is that acetylynic hydrogens are unusually acidic. This is what we call an acetylynic hydrogen. It's basically a hydrogen on a triple bonded carbon. It's a hydrogen that is bonded to an sp hybridized carbon. Basically, that would be from a terminal alkyne. An alkyne, a triple bond that's at the end of a carbon chain. 1-butyne is a terminal alkyne. The carbon-carbon triple bond is between the 1 carbon and the 2 carbon. So that end carbon will have a hydrogen on it. 2-butyne, we would call it an internal alkyne. That carbon-carbon triple bond is between the 2 and the 3. And so there are no acetylynic hydrogens because it's not at the end of that chain. Now, it turns out that these acetylynic hydrogens are unusually acidic, meaning that they can be removed by a base as an H+. The carbon-hydrogen bonding electrons are then left back on the sp hybridized carbon. That triple bonded carbon gets the lone pair that was bonding the carbon and the hydrogen. That makes it a C-. Now, the reason that hydrogens on carbon are not usually acidic is because C-, which would result from taking away an H+, is not stable. Carbon does not like negative charges because it's not electronegative. But in this case, it is okay taking that negative charge. Again, it's because the orbital in which those electrons sit is sp hybridized, meaning that it's got 50% S character, as opposed to any other type of carbon-hydrogen bonds that might have 33% S character if it's sp2 hybridized, or only 25% S character if it was sp3 hybridized. So this carbon having a substantial amount of S character can stabilize the electrons by putting those electrons into that orbital that has high S character and lets the electrons sit close to the nucleus. That means that we have a relatively tolerable negative charge on a carbon. And therefore, we have, for the first time, a carbon nucleophile. And if we have a carbon nucleophile, that means that we can attack some other carbon that has a leaving group and make a carbon-carbon bond. And this is the first time that we've seen that. Now, what kind of base could do this? We need a particular type of base that is strong enough to remove this type of hydrogen. Not all bases are strong enough. Even though this is relatively acidic compared to other hydrogens on carbon, it is not very acidic compared to other, say, hydrogens that are on an acid, like carboxylic acid or something, acetic acid, or hydrochloric acid. So here's a table of pKa's for different types of groups. Here's ethane with its conjugate base. If we were to remove an H+ from ethane, we would get this guy. That negative charge is on sp3 hybridized carbon. That only has 25% S character, meaning these electrons are forced to sit very far from this carbon. That is why we have a pKa of 50. This is not very acidic. Remember, low pKa is acidic. This is really, really, really high as far as pKa's go. So this is not acidic because the negative charge is not stable. As we increase S character from 25% to 33% for sp2, we get slightly more acidic. This negative charge, these electrons get to sit closer to the nucleus, and so it's easier to remove the hydrogen that would result in that. This hydrogen's on ethene have a pKa of 44. Just for reference, ammonia has a pKa of 35. Removing an H plus from ammonia gives NH2 minus, and that is not particularly stable, but it's more stable than this negative charge on carbon. That should make sense. Having a negative charge on N should be better than having a negative charge on C, generally speaking. So it's easier to remove these H's because the corresponding conjugate base is more stable, and that is reflected in the pKa. But look at acetylene. Here's acetylene with its sp hybridized carbon-hydrogen bond. 50% S character means that the negative charge gets to sit very close to that nucleus, and it gives us a pKa of only 25. That means that the negative charge on the acetylene carbon is more stable than the negative charge on the ammonia nitrogen. That means that we can use NH2 minus to remove one of these hydrogens. If we were to start with acetylene and NH2 minus, the NH2 minus would grab the H from the acetylene and put the negative charge onto the carbon. That would move our negative charge from a less desirable position on the N to the more desirable position on the carbon, sp hybridized carbon. However, notice that the pKa of alcohols is about 16 to 18, which means that this negative O is more stable than this negative C. That means that alkoxide bases, RO minus bases, are not strong enough to remove this type of hydrogen on acetylene. So we need a nitrogen base or stronger in order to create what we call this acetylide. So here's how we might do this in a synthesis. Again, the point that we can do this, the reason we're doing this, is so that we can make carbon-carbon bonds for the first time. So here's an acetylene. This is a substituted acetylene. It's already got some R group on it. But here we have a terminal alkyne with an acetylenic hydrogen on it. We're going to use NaNH2 as our base. Again, this gives us an N minus along with an Na plus. And as we know, that N minus is going to grab the H plus, put the electrons back onto the carbon. That gives us the carbon minus instead of the N minus. And again, like we saw, that's better. It's better to have a carbon minus than an N minus. We know that because acetylene is more acidic than ammonia. So that gives us our carbon nucleophile, or C minus, which we call acetylide. We can then take some carbon with a leaving group, an electrophile, and that acetylide will attack our carbon with the leaving group. In this case, the leaving group is the iodide, displace the I, and just like that, we have made a carbon-carbon bond. We used our carbon nucleophile to attack our carbon electrophile, and we made a carbon-carbon bond between the attacking carbon and the carbon bearing the leaving group. Here's an example. We're starting with sodium acetylide, meaning that we started with our acetylene and have already deprotonated our terminal hydrogen with NaNH2. That gives us the acetylide nucleophile. Here's 1-bromobutane, a 4-carbon chain containing a leaving group on the 1 carbon. Our nucleophilic carbon is going to attack the carbon with the leaving group, displace the leaving group, and we make a carbon-carbon bond between those 2 carbons, the attacking carbon and the carbon with the leaving group. That is 1 hexyne. We've now made a 6-carbon chain containing a triple bond between the 1 and the 2 carbon, 1 hexyne. We could also start from ethynyl cyclohexane, meaning it's a cyclohexane ring with an ethynyl group as a substituent. You could also think of it as cyclohexyl acetylene, an acetylene with a cyclohexyl group on it. In our first step, we would use NaNH2. We know that will deprotonate our acetylenic hydrogen, give us our acetylide with the carbon minus on the sp hybridized carbon. Then ethyl bromide, or bromoethane, an ethyl group containing a bromine. Our nucleophilic carbon will attack the carbon on the ethyl group containing the bromine, displace the bromine, and we would make a carbon-carbon bond between our nucleophilic carbon and our ethyl carbon that had the bromine. So again, we are building more complex organic structures from simpler organic fragments. We also would know how to make ethynyl cyclohexane. We could start from acetylene, use NaNH2 to remove the hydrogen, then use bromocyclohexane as our electrophile, have the acetylide react with the bromocyclohexane, displace the bromine, and we get ethynyl cyclohexane. Now, one caution here is to watch out for other acidic hydrogens. If there are any other hydrogens on your starting material that are as acidic or more acidic than the acetylenic hydrogen, then the base will preferentially remove those more acidic hydrogens rather than the acetylenic ones. So that means that our starting material cannot have carboxylic acids or alcohols or any other hydrogens that are more acidic than a pKa of around 25. That's the acidity of our acetylenic hydrogen. So beware of that. If you do, this reaction will not work. Let's take a brief look at carbonyls, which are carbon-oxygen double bonds. Carbonyls as electrophiles that can be used in conjunction with acetylide nucleophiles. This is a carbonyl. Again, here's our C double bond O. We know that that's a polar bond, so the carbon will have a partially positive charge. The oxygen will have a partially negative charge. We can look at the electron potential map and see that there is indeed an asymmetric distribution of electron density there. The orbitals look like this. Our carbon and our oxygen are sp2 hybridized. They are using their remaining p orbital to make the pi bond. In the carbonyl, the highest energy bonding orbital is the pi bond, which means that the lowest energy antibonding orbital, or the LUMO, the lowest unoccupied molecular orbital, is the pi star antibonding orbital. So if we react a carbonyl with some nucleophile, the nucleophile is going to donate the electrons from the nucleophile's highest energy orbital to the electrophile's lowest energy orbital, which again, in this case, is the pi star antibonding orbital, or the antibonding orbital corresponding to the pi bond. So when the nucleophile does that, and the pi star antibonding orbital is populated, the corresponding bond, meaning the pi bond, is broken. So when this carbon receives the lone pair of electrons from the nucleophile, the leaving group is not an atom. The leaving group is the pi bond, the two electrons that correspond, the two electrons that make up the pi bond. So those electrons will leave and they will go on to the oxygen, again, the more electronegative atom of that pair. That would get us an alkoxide. The carbonyl is an extremely useful nucleophile because of two reasons. The first thing is that you can make a carbon-carbon bond using a acetylide, for example, and a carbonyl as our electrophile. You make a carbon-carbon bond, but you also simultaneously generate an alcohol or an alkoxide on that same carbon. Let's take a look. I'll move this mechanism up. Here's our nucleophile adding to the pi star antibonding orbital, breaking the pi bond. The leaving group electrons go onto the oxygen. If we then follow up by adding water or a dilute acid, we can protonate the alkoxide from the water or acid and we get an alcohol. For example, here's an acetylide reacting with an aldehyde or a ketone. The acetylide nucleophile will attack the positively charged carbon of the carbonyl, adding the electrons into the antibonding orbital of the pi bond. The pi bond will break, the electrons will go onto the oxygen. We will make a carbon-carbon bond simultaneously with a alkoxide on that same carbon. We can then follow up with dilute acid, and we get an acetylenic alcohol, a molecule with alcohol carbon on an acetylenic carbon. Notice here that we have made a product that contains an alkyne and an alcohol, which is why it's useful at this point to be able to name molecules that contain both of these functional groups. Here's a practice problem that you can try, synthesizing this compound using the chemistry that I've showed you so far. The prompt specifically says, show how you would make this compound, how you would synthesize it, beginning with acetylene and any other necessary reagents. So you can do any reactions you want. You can do SN1, SN2, E1, E2, free radical. You can do any of the reactions that you know, all the addition reactions to alkenes, any reactions that you know with alkynes, but you have to start with acetylene. And your goal is to make this. You won't be able to do it in one step. You'll have to do it in multiple steps. So figure out what steps you need and figure out what order is most useful for those. We'll go over this in class. Let's turn our attention now to how we would make alkynes. Instead of looking at how we can use them in terms of their acetylenic carbon as nucleophiles, let's look at how we would make them, how we would synthesize them. We can make alkynes by what I call double elimination. We looked at making alkenes by elimination, either E1 or E2. And in doing so, we would make a pi bond. We'd remove a hydrogen with a base and subsequently displace a leaving group on an adjacent carbon. That would give us a pi bond. It follows that if we did that twice, we could get 2 pi bonds, and then we'd have an alkyne instead of an alkene. That is indeed true. If we have for example, vicinal dihalide, 2 adjacent halogens, each one on a carbon that also has a hydrogen, we could eliminate one hydrogen with its adjacent leaving group with a base, so lose HX. This is dehydrohalogenation, and we'd get what we call a vinyl halide. One of our HX is gone. If we had another equivalent of base, another molar equivalent of base, we could do it again. Remove the adjacent hydrogen, the electrons fall in to make the pi bond, displace the leaving group, another E2 type elimination, and we would get a second pi bond, and we'd have an alkyne. This works in 2 steps. You simply need twice as much base as you have starting material. The first elimination happens very rapidly to get to the alkene, in this case the vinyl halide. The second step would take much longer. You're much less likely to remove the H and the X from the alkene to get the alkyne than you are to remove an H and the X from the dihalide to get the alkene. That works with vicinal dihalides, where you take the hydrogen on the left, remove the X from the right, and then remove the H from the right, remove the X from the left, or vice versa. That would work with a vicinal dihalide. It would also work with a geminal dihalide, where you take an H from the left and remove an X from the right in both steps. You'd see the same procedure. You need 2 equivalents of base. The first equivalent would remove 1 HX pair in a standard elimination, and your next base equivalent would remove another HX pair in a slower E2 step, but in both cases you would get the alkyne. The base the type of base that would be appropriate for these reactions would be KOH, potassium hydroxide, at 200 degrees Celsius, or NaNH2 at 150 degrees Celsius. These reaction conditions are sufficient for double elimination. If you don't use two equivalents of base, or you don't use these elevated temperatures, you'll get the first elimination step to get the vinyl halide, but you will not get the second step to get the alkyne. Generally speaking, the first elimination step will involve formation of the transalkene. That is simply because the transalkene is more favored than the cis, and given that we have two hydrogens and two leaving groups, one pair would give the cis, the other pair would give the trans. You're always going to remove the pair at first that would give the trans, because that's more stable than getting the cis. You'll recall when we looked at addition reactions of alkenes, we compared the energy of a sigma bond to the energy of a pi bond. We can do the same thing for alkynes. These numbers here for the single bond, the double bond, and the triple bond is the amount of energy required to break the bond. So we saw that for a single bond, it required 347 kilojoules. To break a double bond, it required 611 kilojoules. That means that the sigma bond was 347, but the additional pi bond was 264. This is energy required to break it. And remember that lower energy required to break it means it's a weaker bond, so higher energy. We can do the same thing for a triple bond. For a triple bond, the total energy is 837 kilojoules, requires less energy still to break that second pi bond. This means that we can do addition reactions in a similar fashion to alkynes as we did to alkenes. So if we had a triple bond, we can add a electrophile across one of those pi bonds, use 2 electrons from our electrophile sigma bond and 2 electrons from our alkynes pi bond to make the 2 new bonds, C to A and C to B. We can do that once with one equivalent of AB. If we add another equivalent of AB, we could add it twice across that carbon-carbon bond using the 2 pi bonds. For example, if we did hydrogenation, H2 and platinum, we could add H2 across the first pi bond, and then with a second equivalent of H2, we can add another across the second pi bond. Now, notice that this is in brackets. That means that this intermediate cannot be isolated. That is to say that when you do hydrogenation of a triple bond with H2 and platinum as your catalyst, you cannot stop at the alkene. There is no way to control the addition of the hydrogen in such a way that you only get the alkene and not go all the way to the alkane. The always, your product of hydrogenation of a triple bond with H2 and platinum will give you the alkane as the product. So wouldn't it be nice if there was some way to stop at the alkene? What if there is some way to only hydrogenate one of the pi bonds, that is to say, the higher energy pi bond, the second pi bond, and leave the lower energy, this more stable original pi bond, the first pi bond? Well, it turns out that there is a way to do it. You do not use H2 and platinum. What you need is a slightly weaker catalyst, and that catalyst is called Lindlar's catalyst. Lindlar's catalyst is a kind of a witch's brew of many different reagents. It requires H2 for our hydrogenation, but instead of platinum, we use palladium on barium sulfate along with quinoline, which is this polycyclic aromatic compound, and methanol. This entire mixture, except for the H2, everything besides the H2, is called Lindlar's catalyst. It's sometimes called a poisoned catalyst because the addition of these other reagents causes the catalyst to be able to hydrogenate the higher energy pi bond, but it's been poisoned, so it's a weaker catalyst, and it will not hydrogenate the other pi bond, so it will not hydrogenate the alkene. Furthermore, if you recall the mechanism for hydrogenation, remember that the hydrogens get kind of absorbed onto the surface of the metal, and then when the pi orbitals kind of come in contact with one face of those orbitals coming in contact with the surface of the metal, the hydrogens add on to that one face of the alkene, and that gave us syn addition of the hydrogens in hydrogenation. The same mechanism applies in Lindlar's catalyst because we're still using hydrogen adsorbed onto a metal catalyst. So we get the hydrogens adding to the same face of the triple bond, and that means that we always get the cis double bond. The alkene will always be in the cis geometry when you hydrogenate an alkyne with Lindlar's catalyst. There is also a way to do that with the transalkene being the main product, but it requires a different reagent, not surprisingly. This reagent is sodium and liquid ammonia, Na/NH3. Now, this is two different components, sodium metal and liquid ammonia. It's written as Na/NH3 because the sodium is actually dissolved into the ammonia. Sometimes it's called a dissolving metal reduction or a metal ammonia reduction. This is different than NaNH2. Don't confuse the two. NaNH2 was Na plus NH2 minus. It's an ionic compound that was a very strong base. That's what we use to deprotonate acetylynic hydrogens. But this is Na metal dissolved in NH3 liquid. This is done in very low temperatures because sodium metal is extremely reactive. And at such low temperatures that are required to make sodium easy to deal with, we end up having ammonia being in the liquid state. So here's the mechanism. It begins with an electron from sodium. Remember, sodium has that one lone electron out in the 3s orbital that it wants to get rid of to make its electron configuration look like neon. So sodium will give off a single electron. That electron will add to a carbon involved in the alkyne, and that carbon will give up the pi bond to the other carbon in the form of a lone pair. That gives us what's called a radical anion. You've got the radical from the single electron from the sodium, and we've got an anion on the other carbon. Now, in this step, we already are generating a trans double bond, a trans geometry. The radical and the anion will position themselves as far away from each other as they can, and the R groups will then end up, whatever these groups are, will end up as far away from each other as they can. In the next step, the anion will get protonated from our ammonia to give a vinyl radical. We will protonate our carbon. We'll end up with a vinyl radical and NH2 minus. Then we're going to repeat that same sequence of steps again. We're going to take another electron from another sodium. That's going to add to our half-filled orbital and turn our radical into an anion. So now we have a vinyl anion, an sp2 hybridized anion. And then lastly, we will protonate that anion from ammonia and we get our transalkene. So we have two ways to partially hydrogenate a triple bond. We can do it with Lindlar's catalyst to give us the cis. We can do it with a dissolving metal reduction to give us the trans. If we want a full hydrogenation from the alkyne to the alkane, we would use regular H2 and platinum. We can also do addition of halogens to alkynes, kind of the same way we did additions of halogens to alkenes. If we start with an alkyne and we add one equivalent of Br2, for example, we're going to add the Br2 across the pi bond in the same fashion we did to alkenes. We're going to get mostly trans addition of the Br2 across the pi bond. we're going to get some cis addition. It's going to be about 70-30. If we do two equivalents of halogen, so meaning we do first one addition to give us the trans and cis mixture, then we do another equivalent of halogen, what we end up with is the tetrahalo product. So we will first get the trans and the cis, then we will further halogenate the double bond to get the single bond, use up both of the pi bonds to add our halogens. So one addition to give mostly trans but some cis, another addition to give the tetrahalo product. This is the same mechanism as the alkenes. Go back and look at addition of Br2 across a double bond, and it's the same mechanism as it is for a triple bond. Along that same line, we can also add HX across a double bond. Remember, this was Markovnikov addition, where you added H to the carbon with the most H's and X to the more substituted carbon. The same rules apply for addition to a triple bond. If we have an alkyne, and notice that this does need to be an asymmetrical alkyne. In order to get Markovnikov orientation, you have to have a clear preference for one carbon being more substituted and one carbon being less substituted. So we're going to add HX across our asymmetrical triple bond. We're going to add the H to the carbon with the most H's, and we're going to add the X to the carbon that is most substituted. That is Markovnikov's rule. Now, we had two pi bonds, and we're going to use one pi bond in order to add the HX. So we will still have one pi bond left over. If we add another equivalent of HX, we're going to do the same thing again. We're going to follow Markovnikov's rule and add H to the carbon with the most H's. That's going to get two H's onto our less substituted carbon. And then we're going to add X to the more substituted carbon. So we're going to have two X's on the more substituted carbon. Here's one pentyne, another asymmetrical alkyne. We say, okay, the Markovnikov position is the more substituted carbon. So we're going to add the bromine there, and we're going to add the H to the carbon with the most H's. That's one addition. We could do a second addition to here if we added another equivalent of HBr. If we have two pentyne, notice that we don't really have a Markovnikov position. Each carbon on the triple bond has one carbon attached to it. Now, one side's a methyl and one side's an ethyl, but as far as substitution goes, each carbon on the triple bond has one carbon on it. So we don't really have a preference here. If we're going to add the H to the carbon with the most H's and follow Markovnikov's rule, well, neither carbon here has more H's on it. So we can get both orientations. We could add the bromine to the carbon with the methyl and the H to the carbon with the ethyl, or we could add the H to the carbon with the methyl and the bromine to the carbon with the ethyl. And in both cases, we will also get E and Z isomers. The E will probably be more favored because usually E is more favored over Z because it's more sterically less sterically hindered. But either way, we get four potential products. We get two constitutional isomers, the 2-bromo versus the 3-bromo, and for each constitutional isomer, we get E and Z stereoisomers, the geometric isomers. We can also do hydration of alkynes. The same way that we did hydration of alkenes in a Markovnikov or an anti-Markovnikov fashion, we can also do hydration of alkynes in a Markovnikov or an anti-Markovnikov fashion. There is one catch, though, for addition of water across an alkyne. Here's the kicker. Here's our alkyne, and we're going to use water along with HgSO4 and H2SO4, so mercury sulfate and sulfuric acid. This is the similar mechanism as oxymercuration demercuration was for addition to alkenes. It's the same, we use mercury in the same way to ensure that we get Markovnikov orientation of the OH across the double bond. So here's our pi bond. We're going to use up our pi bond to add water across that. We're going to put the OH on the Markovnikov position and the H on the carbon with the most H's. So again, this follows Markovnikov's rule. But this guy in brackets is not our final product. This is not a stable molecule. This is something called an enol. This is specifically an alcohol on a carbon that is double bonded to a carbon. We call this an enol because it's an alcohol on an alkene. The vinyl alcohol is not stable, and it will undergo something that is called tautomerization. And it turns, look what's going on here. It turns the oxygen in the alcohol into a double bond O, and the H that was on the alcohol ends up on the other carbon. And we end up with no more double bond there. We end up with a single bonded carbon here, and the two H's on one and the double bond O on the other. That process is called tautomerization. I'm going to show you what's going on the next slide. But just remember that the enol is not stable, and so it will transform the enol into the ketone. Here's the mechanism. We're going to add our mercury to our alkyne, and we're going to position the mercury on the less substituted carbon for two reasons. First of all, the Hg is big, so we need more room for it. So we're going to put it on the carbon with the smallest groups, that is to say, the hydrogen. That also gets us a vinyl cation. This C plus is on the more substituted carbon. We always want positive charges on the more substituted carbon. Now, when we did the oxymercuration demercuration, we made the mercurinium ion, which means that Hg plus fed back into the other carbon, and we got a three-membered ring. The reason that that doesn't really happen in this case is because of the double bond geometry. That double bond wants to have 120-degree bond angles on those carbons, and that makes it really hard for that mercury to grab that other carbon. You can imagine it doing so if the parallels help you remember it, but technically speaking, the mercury does not make that mercurinium ion. But then what happens is we add water to that carbocation, kind of like the second step of an SN1 reaction. Water's going to attack. That's going to give us our water on our carbon with a positive O. We can use another molecule of water to remove that extra hydrogen, and that gives us our Markovnikov positioned alcohol with the Hg on the other position. That's an organomercurial alcohol. In the second step, what happens is the double bond gets protonated by some acid. Again, we've got HgSO4 and H2SO4, so that's sulfuric acid. We're going to protonate that double bond. That gives us a resonance stabilized intermediate. And what's going to happen is the mercury is going to leave. Basically, the mercury is going to fall off, and it's going to donate its electrons back into that carbon-carbon bond, and we're going to regenerate our alkene. That is our vinyl alcohol, the enol. But like we said, that is not isolated. That is not a stable product. Remember, we said it's going to tautomerize. Here's what that tautomerization looks like. There are two forms of an enol. Basically, there's the enol form, where we have the double bonded C with the hydroxy group, the alcohol group, on one of those. And the tautomerized form moves that H from the oxygen to the other carbon. And the carbon bearing the oxygen ends up with a double bond O. We call that keto-enol tautomerization. There's an enol form, which is the alcohol form, and there's the keto form. We call that keto because it looks like a ketone. It is almost always the case in a keto-enol tautomerization that the keto form is preferred. There are some very specific cases where the enol form is preferred. Usually it involves that double bonded carbon being trapped in an aromatic system such that it does not want to tautomerize to the ketone because losing that double bonded carbon would lose the aromaticity of the molecule. That's usually the cases where enol is preferred over ketone. But under normal conditions where major kind of stabilizing factors are not present, the keto form is favored. Here's the mechanism for tautomerization. Here's our enol, which again is not stable. We're going to protonate our double bond. Our double bond is going to grab an H plus from solution. Again, we are in acidic conditions here. And we're going to add the hydrogen to the carbon that does not have the oxygen on it. So we're going to add it to our less substituted carbon. Again, we're going to add the H to the carbon with the most H's. That kind of what Markovnikov said. The reason we do that is because that gives us a positively charged carbon bearing an oxygen. And that oxygen can donate electrons back into that carbon to resonance stabilize that cation. We can delocalize that positive charge off that carbon and onto the oxygen. Again, 2 resonance forms is better than only 1 form. Notice that the right form of this resonance structure has every atom with an octet. So we actually are able to form a more stable structure by delocalizing that positive charge. Then, from that more stable form of the resonance, we can grab an H off of our oxygen. Something like water can grab an H off of that oxygen and return those electrons back to the O. That then traps our oxygen in the double bonded form, and we end up with our hydrogen again on that other carbon. Therefore, we have transformed our enol into a ketone. So protonate our double bond, draw the resonance structure that gives us a double bonded O, and then remove the H from the double bonded O, and we are left with a ketone. Anytime you make an enol, you can expect it to tautomerize to the ketone. Notice then that rather than adding water across this, in terms of an OH and an H, we are adding a double bond O to the Markovnikov position and 2 H's to the less substituted carbon. So this is hydration, but it's not really hydration. It's actually turning this into a ketone. Again, the carbonyl ends up in the Markovnikov position after enol tautomerization. We can take 1-butyne, again, a asymmetric alkyne, where we have a clear distinction between the Markovnikov carbon and the anti-Markovnikov carbon. We're going to add our reagents for this, water, HgSO4 and H2SO4. We're going to add our OH to the more substituted carbon, the Markovnikov carbon, and we're going to add the H to the carbon with the most H's. That's going to get us an enol, which will then tautomerize. We're going to move the double bond from the CC to the CO, and we're going to move our H on our O back to the other carbon, and that gets us a ketone. We still got our 4 carbons, 1, 2, 3, 4, 1, 2, 3, 4, but instead of the triple bond, we end up with the double bond O on the more substituted carbon. Just a quick summary here. We can do hydrogenation, full hydrogenation of a triple bond to an alkane using H2 and palladium or H2 and platinum, some non-poison catalyst. If we want our hydrogenation to stop at the double bond and not go all the way to the single bond, we can do it 2 ways. We can use the dissolving metal reduction, Na with NH3, to get us the trans double bond or the E. We can use H2 with Lindlar's catalyst to get the cis double bond or the Z. That's our poison catalyst. We can add 1 equivalent of X2 across the double bond to get an alkene With our X's trans, or E, adding one equivalent. If we add two equivalents, we're going to saturate this by adding all four of our X's, X2 twice, across our two pi bonds to get the alkane. That's the tetrahalo product. We can add HX across the pi bond. If we have one equivalent, we're going to follow Markovnikov's rule once, adding our H to our carbon with the most H's and our X to the more substituted carbon. That would leave us with one pi bond. If we add another equivalent, it will add Markovnikov again across the remaining pi bond to give us basically double Markovnikov addition, adding the H's to the carbon with the most H's and adding the X's to the more substituted carbon. If we do Markovnikov addition of OH across the pi bond, we do HDSO4 with H2SO4 and water. We're going to add OH to the Markovnikov position. We're going to add H to the carbon with the most H's. That is an enol that we know that is unstable, and that will tautomerize to the double bond O. That we get the Markovnikov double bond O. We are making a ketone here. We can also do anti-Markovnikov addition of water. Remember when we did anti-Markovnikov addition to an alkene, we did hydroboration oxidation using BH3THF, then H2O2 and hydroxide. The parallel reaction for alkynes is very similar. We're going to take our alkyne, again, an asymmetrical one where we have a clear preference for Markovnikov and anti-Markovnikov. Instead of using BH3THF, we're going to use a similar but slightly larger and more bulky boron, alkyl boron group called dicyamylborane. The cyamyl group is also called sec-isoamyl. It looks like this. It's a 1, 2, 3, 4, 5 carbon branched alkyl group, and we have two of them. So it's dicyamylborane. The first step involves addition of the dicyamylboron to the less substituted carbon. Remember that is the same kind of logic that we used for anti-Markovnikov addition of OH to an alkene. The boron went on the less substituted side because there was more room for it. The H added to the other side. So now we have our boron group on the anti-Markovnikov carbon. We added our H to the carbon with the fewest H's. That's anti-Markovnikov. In a second step, looks similar to what we did for hydroboration oxidation of alkenes. We had H2O2 and hydroxide. We're going to oxidize that dicyamylborane to an OH, but that gives us an enol again. Only now the OH is on the less substituted carbon. That will then tautomerize to the carbonyl on the less substituted side, which gives us an aldehyde now instead of a ketone. Remember before, when we added the carbonyl to the more substituted carbon, we got a ketone. We added the carbonyl to the more substituted carbon, we got a ketone. Here, when we add the carbonyl to the less substituted carbon, we get an aldehyde. Two different functional groups. Notice that this will tautomerize under basic conditions as well. Before, when we did a tautomerization for the Markovnikov form, we had acidic conditions, and we did tautomerization in acid. We can also do tautomerization in base. Here's the mechanism for base catalyzed ketoenol tautomerization. First, remember last time what we did was we protonated the alkene because we had acid. If we don't have acid but we have base, what we're going to do is deprotonate the OH. This is like an alcohol, so it's got a fairly low pKa. It's fairly acidic. So we're going to deprotonate that H, put the electrons back onto the O. That gives us a resonance stabilize what we call an enolate. It's the anion of an enol. So here's the double bond O. We can take these electrons, move them down to give us a C double bond O, then move the pi electrons from the C double bond C onto the other carbon. That gives a resonance stabilized negative charge. It's not trapped on the O, it can be delocalized onto the C. Obviously, it's better to have the negative charge on the O than the C, but at least we can spread out the negative charge a little bit. Then, from that other resonance form where we have the double bond O and the negative C, we're going to reprotonate our carbon. We're going to take the water that we just made from protonating our hydroxide, and we're going to protonate our carbon from that water. That's going to regenerate our base. It's going to trap our carbonyl in the carbonyl form, and notice that we have migrated our H from the OH, oxygen, to the other carbon. That is tautomerization, and we did it under basic conditions or acidic conditions. There are several ways to oxidize alkynes. All of them involve KMnO4. Remember, I told you that KMnO4 is a promiscuous reagent. It will react with all kinds of reagents in all kinds of different conditions to give all kinds of different products. Here is how it works with alkynes. If we use KMnO4 neutral on a symmetrical alkyne, notice that we have two R groups on our alkyne. What we will do under KMnO4 neutral conditions is convert the carbon-carbon triple bond into two ketones. Each carbon that was involved in the triple bond ends up with a double bond O. If we add KMnO4 under basic conditions with heat, we will cleave the triple bond, and each carbon that was involved in the triple bond will end up with carboxylic acids. So these two carbons there and there were connected, and instead of being connected now, they have double bond O and single bond O with an H. So we can cleave the triple bond to give carboxylic acids. That's exactly what we did with double bonds. KMnO4 basic and heat. We cleave the double bond and ended up with carboxylic acids. If we have an asymmetrical alkyne where one of them has an H, notice what happens. If we cleave that, the side with the R just becomes a carboxylic acid, a normal carboxylic acid. But the side with an H ends up with two carboxylic acids. This is carbonic acid, and it will decompose into carbon dioxide and water. So that will go away. The water will ostensibly boil off from the heat. The carbon dioxide will bubble away because it's a gas, and all we will be left with is just one equivalent of our carboxylic acid. The other carbon on the other side of the triple bond we lose. If we have an asymmetrical alkyne with KMnO4 neutral, same thing is going to happen. We're going to get double bond O's on both carbons that were involved in the triple bond, but instead of having the H left on one side, that will get oxidized to the OH. So just keep that in mind. Neutral conditions, the C triple bond C turn into two C double bond O's. If we have any H's left on our carbons, they will also get oxidized to O's. If we use basic conditions in heat, we're going to cleave the double bond, convert everything into carboxylic acids. If we end up with the diacid, the carbonic acid, that's just going to decompose and go away. So here's our reaction map again. Remember that we did full hydrogenation, H2 and platinum. Partial hydrogenation to trans was the dissolving metal reduction. Partial hydrogenation to cis was Lindlar's catalyst. We could add one equivalent of Cl2 or X2 across our triple bond to give mostly trans, but some cis, or if we did two equivalents of our halogen, we'd get the tetrahalo product. If we have an asymmetrical alkyne, we could do several things. We could do anti-Markovnikov addition followed by tautomerization to give the aldehyde. We could do Markovnikov addition followed by tautomerization to get the ketone. We could do oxidation under neutral conditions to give us a ketone and a carboxylic acid, or we could cleave it to give two carboxylic acids if we did KMNO4 basic with heat. We could do double elimination of geminal or vicinal dibromides. Also on here, if we have an asymmetrical alkyne, we could also do the Markovnikov additions of HX. That's not on here. So maybe you want to add those. If you're adding your notes, add Markovnikov addition of HX across our asymmetrical alkyne. You might want to fill in these reagents so that you know which one goes where. If you want more practice, the Stromanis chapter for lecture 13 is chapter 11. And again, if you're following in the Wade textbook, this is Wade chapter 9.